Welcome to section 3.4, where we're going to look at solving exponential and logarithmic equations and inequalities. Now that we've looked at ways that we can use logarithms in our calculators to find the logarithm of any base, there's many more types of equations that we can now solve. Where before we could either estimate or we weren't really able to solve them specifically. One of the strategies we can use when solving exponential equations is to rewrite them so that they have a similar base. Of course, not all equations can be solved this way, but there are some that can be, so we're going to look at that as one of the strategies we can use. For example, here I've got 25 to the x power, and then it's equal to 125. Looking at these, we can see these have a common root of 5. So let's see what we can do to rewrite these. For example, we know 25 is 5 squared. So that's 5 squared. And then, remember, that's being raised to the x power. And 25, or 125, is 5 to the third power. And whenever we have a base with a power raised to a power, as we have on the left here, we can multiply those exponents, so we can write this as 5 to the 2x, and we can, this is 5 to the third. So we've rewritten these with the same base of 5 on both sides. And so in order for these to actually be equal to each other, which is what our statement says, is the x value over here needs to be what I would need. The x value needs to be such that these two will result in the same power, right? These two will really result in 3. Because the only thing that's equal to 5 to the third is another 5 to the third. So I want to figure out, how does 2x, what value for x will make 2x equal to 3? So we're kind of just rewriting this and focusing in on the exponents there, because I know for these this statement to be true, that the two exponents have to equal each other. And so then we can solve this for x, and we see that that works, that 2x would be equal to 3 when x is equal to 3 halves. And so this is the solution to the exponential equation that we have. When x is equal to 3 halves, 25 to the 3 halves power will equal 125. We can kind of try that out here. 25 to the 3 halves. Remember that the denominator would be a root, so this would be the square root of 25 because of the 2. That's a square root, and then we raise that to the third power, the numerator there of the fractional exponent. And the square root of 25 is 5, and 5 to the third is 125. So we can see that 3 halves is the solution to this equation. Looking at the next one here, again, we see a common root there of 3. If I rewrite the left-hand side, that's 3 squared raised to the x power, and here we have 3 to the x plus 1, and any base with a power raised to a power, we can use the power rule. That's 3 to the 2x equal to 3 to the x plus 1. And so now with the same bases on each side, we can focus on the exponents, figuring out how 2x can equal x plus 1. And if I subtract x from both sides, we see that's 2x minus 1x, or x equal to 1. So in other words, when x equals 1, our two sides of that equation will be equal to each other. And so if we check that, we can see, all right, 9 to the 1 equals 3 to the 1 plus 1. So 3 to the 1, I'm sorry, that's 9 to the 1, not 3 to the 1. I rewrote that wrong. So we have 9 to the 1, that's more like it, equals 3 to the 1 plus 1, so that's 9 on the left-hand side, and 3 to the squared, which also is 9. So 1 appears to be the correct solution for this exponential equation. So that's one strategy we can use. Obviously, this would be limited in its scope to only these that are kind of set up for us where the two sides do have a similar base. But what about situations where we have different bases and or we don't have similar bases on either side that we can just rewrite them as? So there are some steps that we use with exponential equations, kind of step-by-step approaches to solving these. The first one being we want to isolate the exponential expression onto one side of the equation. So I'm going to rewrite this here, but we have solving for x 5 times. You may actually see this sometimes written with the parentheses. So here it's written with a dot. I'm going to write it with the parenthesis. 2x minus 3 equal to 17. So step 1, if I'm going to isolate this, I'm going to just move this up here. Well, the one thing that's keeping the exponential part not isolated is this multiplication by 5. Right? This 5 here, if this wasn't here, this exponential expression here would be isolated. So I'm going to get rid of the 5 by doing the opposite. It's being multiplied, so I'm going to divide both sides by 5, and I'm going to leave this as a fraction. So this gives me 2 to the x minus 3 equal to 17 fifths. Now, you can sometimes write this as a decimal. If it's one of those that repeats forever without a pattern, that type of thing, you want to take it out several decimal places. But with our calculators, we can actually leave it as a fraction as well. That way, it's always exact rather than being approximated. Now, 17 fifths actually is 3 2/5, which is 3.4. But so either way we did it, 3.4 is an exact outcome. So that is an exact. It's not rounded. It's not approximated. But regardless, for this, now we're going to use logarithms to help us solve it. When we take the logarithm of both sides, it's going to provide a way for us to get the x where we see it up in the exponent out of the exponent. So if I do that, let's say I'm going to take the natural log, but you could do the same thing with common logs, which is base 10, where natural log is base e. We can now rewrite this out in front, and that takes it out of the exponent, x minus 3. Keep that grouped. Use parentheses there. So we have x minus 3 out front multiplied by ln of 2 equals the ln of 17 fifths. And in trying to solve for x then, I could divide both sides by the ln of 2. That cancels this over here and leaves me with x minus 3 equal to this mess here, ln of 17 fifths over ln of 2. And then finally, I need to just add 3 to both sides. So what we have is x is going to be equal to the ln of 17 fifths divided by the ln of 2 plus 3. So now it's just a matter of putting this into our calculators and solving for x and getting an approximate outcome. And you should practice putting this into your calculator, but the answer is approximately 4.7655. It's a sloppy looking 4 there. But there's our solution for this equation. So logarithms provide us with that opportunity to solve equations where the bases are not going to be the same. And that's pretty much going to be the case most of the time. Again, if we start with this equation here, 5 to the x, 2x minus 3 equals 3 to the x plus 1. We can see automatically, we don't have to even do a whole lot here, that the bases are very different. On the previous one, we just had it set equal to a number. But here we have two exponential statements on either side. So they're both isolated, which was our first step on the previous. But regardless, as long as we got one side isolated, whether there's just a number over here and it's not an exponential expression, but this one is an exponential expression, we always want to get one, wherever the exponential expression is, get it isolated on either side, on one side of the equation. And once we've done that, this is where we take either the natural or the common log. I'm going to take the common logarithm here. Not for any particular reason, because they'll both work. I just want you to see that it works on both sides. So we're taking, it works with both methods. So again, we're taking the log of a base raised to a power. We can rewrite that as, with the power rule, 2x minus 3 times the log of 5 equal to x plus 1 times the log of 3. And now we basically want to try to get stuff to one side of the equation. Our next step here then, in kind of unwrapping all this, you'll notice this expression that we have here has an x as well as this one. So we actually want to distribute our logs here, and we can do that because, well, it's being multiplied, so using the distributive property we can do it. Notice that I want to differentiate this between one of the things we don't do is when I'm taking the log of a sum, which is not what I'm doing here because I'm taking a log of this number, that I don't rewrite this as log of m plus log of n. In other words, I don't distribute the log and take the log of this sum. Here, these outcomes are just going to be exponents. Coefficients. They're going to be out front. In other words, this would be 2x times the log of 5, which the log of 5 is just going to be some number, minus 3 times the log of 5. Again, log of 5 is, so it'd be like distributing a 2, right? But the log of 5 is not 2, but it's the same thing. It's a constant value that we have that we're distributing. And so then we have here x log of 3 plus 1 log of 3, which is just log of 3. What this has done now is it's isolated two specific terms that have a log in them. The others are just numbers, right? That whatever the log of 3 is, it's a number. And so what I want to do is to get the terms that have x to one side of the equation. So we're going to subtract x log of 3 on both sides. We're subtracting it here. And then I'm going to add the 3 log of 5 to both sides. Now over here, it gets rid of that. So all I have left on the left side of the equation now is the 2x log of 5 minus x log of 3. And on the right-hand side, we subtracted this, so I'm just left with positive log of 3 plus 3 log of 5. So now the two terms that have x are over here on the left-hand side, and then there's no x's over here. So in every equation we're trying to solve for x, both of these have an x as a common factor. This is 2 times x times log of 5. This is x times log of 3. So x is a common factor that we can factor out on the left-hand side. So taking the x being a common factor across this subtraction, we're going to rewrite this with x out front. So x times, and what I have left from the first group here is 2 log 5. And then what we have left over here is just log 3, subtracting log 3. And everything over here is the same. I can't combine these because that's log of 3, log of 5. Those are two different outcomes. So we just leave that as log of 3 plus 3 log of 5. And then to solve this, we're going to divide out that entire parenthesis, divide both sides by 2 log 5 minus log of 3. And that whole statement there goes away. And on the left-hand side, we just have to mirror that. 2 log 5 minus log of 3. So my x outcome here is x equal to, and I've run out of room here, so we saw that this canceled out, became 1. So basically what I have left over there is my solution, x equal to this whole thing. Now, in my calculator, I'm going to type this out. You have to put a parenthesis, since this is a sum on top and a difference on bottom, your calculator, you need to group that because we want this sum. Remember that plus and minus are the last things in the PEMDAS hierarchy of what we do first. And so I need to tell my calculator with parentheses that we want this sum done, and then we want to divide, and then I want the result of the subtraction, so I need to put the subtraction also in parentheses. So with me, go ahead on your calculator and let's get a decimal approximation of this. As you're typing, keep in mind when you hit log or ln, if you used ln, you would get the same result if this was in ln. When you type log, it opens up a parenthesis that you have to close to tell the calculator, basically, take the log of this, right? So as you're typing, you're going to have some double parentheses. So you got to start out with a parenthesis, then log 3, close that, plus 3 log parenthesis 5, close that parenthesis, and then close the top parentheses. So that this parenthesis pairs up with another parenthesis, right? And you can see the inners are just of those. So this can be tricky. That's why I want you to practice typing this in. And you can pause this, or just to compare, you want to compare. What you should get is 2.795, approximately 2.795 as your answer for this particular logarithmic or exponential equation that we used logs to solve for. In this one, we're going to look at one that's a little more tricky when we start to try to evaluate it. And you can, with this equation, if you started trying to, get x by itself on one side, you're quickly running into a bunch of situations where it just isn't working. And in that case, we need to come up with an alternative way of solving it. So in this one, it's kind of up to us to recognize that this fits into a quadratic form. And of course, this says it up here, quadratic form, right? But without that suggestion, you may not recognize that. So when we say quadratic form, we want to look at the exponents that we have here. I have a 2x, and then I have an x, and then I have no x term. And if you look at the coefficients there, you can see the 2, the 1, and then this would be a 0x, which 0 times x is 0, so we wouldn't have an e here. It would be e to the 0, which is 1, and so that would just leave us with the 5. In other words, remember that quadratic equations generally have that shape to them, or that that pattern to them, where we have 2 and then 1 less than that, so 1x, so it's usually squared, and then 1, and so you just have one of the bases, usually the one's not even written, and then you don't have that base there. And let me just draw another one. Let's just say this could be similar to x squared minus 4x minus 5. Okay? Where we had the x squared, then we had 4x to the 1. But here the x is the variable, right? But here the x is in the exponent. So at any rate, this follows an exponential pattern. And so what I'm going to do is a temporary substitution so that we can solve this and we can see it more from the lens of an exponential equation or of a quadratic equation and solve it that way and then take it back to exponential. So we're going to do something called a u substitution where I say, okay, let's say u, and generally with these quadratics, you want to set it equal to the middle term, not the 4. The 4 is just a coefficient there. We're just going to say u equal to e to the x. All right, so if u is equal to e to the x, then if I square u, all right, so we square the left-hand side, then I would square the right-hand side, so e to the x would be squared. This would leave me with u squared equals e to the, using the product, or yeah, using the power rule, 2 times x, right? E, base e of to the x power raised to the second power gives me e to the 2 times x. So, so we have two things we can substitute in here. I'm going to put in the front, notice that u squared is equal e to the 2x, which is exactly what I have here. So I'm just going to temporarily put in u in its place. And then secondly, we have 4 times e to the x. Well, we see e to the x is equal to u, so this would be 4u. And I just picked u because this kind of thing is called a u substitution, and it's something we use in calculus a lot, so it's good opportunity to introduce that here. Notice that when I did this substitution, and remember I picked u being equal to the second thing. If this is a quadratic, then yeah, you have a quadratic situation. We have u to the second minus 4u to the first, and then the constant by itself, which would be a u to the 0. U to the 0 would be 1, so we'd end up with 5 times 1, which is just 5. And now I can look at factoring this. Right? It's a polynomial, and it's a negative. So I know that the signs have to be positive and negative, and 5 and 1 give me a positive 1, negative 5u gives me negative 4u. So my two substitutional solutions for u is u equal to negative 1 and equal to positive 5. Now, this is not x. Remember, I'm solving not for u, but for x. So now we want to take it back to what u was really equal to, right? We said that u equals e to the x. I'll write that twice here. U equals ex. Now let's take the solutions for u and figure out what they would be for x. So we'll start off with negative 1. Instead of u, we'll put negative 1 equals e to the x. So in other words, e to what power is going to give me negative 1? Well, and then over here we have 5. Oops. Over here we have 5 equals e to the x. Now, e, remember, is this 2.7 number. There's no way I can take this number and raise it to a power where I end up with something negative. So this is not going to give me anything worthwhile. Also, if you, let me just take that back. If we take the ln of both sides, we're taking the ln of a negative number, ln e to the x. And so I end up with x equals something that's impossible. If we type in ln of -1, we will get an error. So we see that eventually, if we don't recognize that right away, that cannot be a solution. For the other one, however, let me get this arrow out of the way. If we take the ln of both sides, that gives me ln of 5 equals ln of e to the x. Remember, ln is log base e. And so whenever we have log base here, similar with the base there, we know the answer is x. That's one of our properties of logarithms. And so we see x is equal to the ln of 5. So that itself can be our answer. If they want a decimal approximation, then we just type it into our calculator, and we see that the ln of 5 is approximately 1.609. Either one of those this is an exact answer, and this is a rounded, so therefore approximate solution. That one was kind of tricky, so I wanted to work another one that's like that. This one's even a little more obscure, harder to recognize, but we do see it going from like x to like negative x, which that's a two-step thing. Remember, we're always going from, to the 2, to the 1, to the 0. So this is going from the 1 to the 0 to the negative. So one of the things that we can do to fix this, now these are three different terms. We have this. It's harder to see because we put that 8 times and there's that space there, but this is one term. It's one product, so one term, and then we have this constant over here. What we really want is something to the second power, right? Going back, we can see we wanted that sort of to the 2x thing going on, and then the x, and then the 0. It's harder. That's why it's harder to recognize here. But if I multiply through by another 3 to the x, so I multiply both sides by e to the x. I'm sorry, not e. I meant 3 to the x. So I'm going back to the previous problem. 3 to the x. I want you to see what happens. And again, this is a little bit harder to see, but this gets distributed. And so that is 3 to the x times 3 to the x, right, for the first multiplication here. 3 to the x times 3 to the x. That's 3 to the 2x. And then we have 8 times, so minus 8 times 3 to the x times 3 to the minus x. Same bases, we're multiplying the bases just like we were here, so we add those exponents. X plus x gave me 2x here. Here, x plus minus x gives me 0. So 3 to the 0. And then on the other side, we've got 2 times 3 to the x. So 3 to the 0, of course, becomes 1. So let's write out what I have here. I have 3 to the 2x. We have minus 8. 8 times 1 now is just 8. And then on the other side, I have 2 times 3x. That's a product. And so we don't want to separate those. You could even write it like so, which makes it seem a little less separated. All right, and so we have that 2, 1, and then 0 now. If I bring this to the other side, so subtract 2, 3 to the x on both sides. I'm going to put it in the middle here, so it's kind of that, it's going downward. So now I have 3 to the 2x minus 2 times 3 to the x minus 8 equals 0. Now we set our u equal to 3 to the x. So that u squared is going to be 3 to the x squared, which is 3 to the base 3 to the x power raised again to the second power. That's a power to a power. So we multiply those two, it becomes 3 to the 2x. So you can see for my first one, that's my squared. I have u squared I can put in here in substitution of 3 to the 2x minus 2u and then minus 8. All I did was take out, and this is, again, a temporary substitution so that this looks more familiar to us. And now I can factor this, and we hope that it factors, but if it didn't, we could use some of the other options that we have, but in solving quadratics. U and U, let's see, plus and minus, because we have a negative 8. And 4 and 2, I think, are going to give us our best, with the 4 being with the negative, because 2u plus negative 4u would give me minus 2u, which is what I have here. All right. So the u values are u equal to negative 2. That's a solution. And then u equal to positive 4. So negative 2 and positive 4 are my two used solutions. Let's find the solutions for x. Remember, u equal to 3x, 3 to the x. And I'll do that again. U equals 3 to the x. We'll put both of those in there. Negative 2 equal to 3 to the x power. And then 4 equal 3 to the x power. Notice all I did here was we have negative 2 and 4 equal to u. And so I'm taking out u, and I'm putting 4 in its place. And I'm taking out u here and putting negative 2 in its place. And now we can solve these for x. Well, again, we run into the same problem here. If I take the ln of both sides, I end up with ln of a negative number. And so that's a problem. I can tell here that I'm going to run into an issue, so I know that this is a non-solution. ln of negative, you cannot take the log of something negative. Over here, if I take the ln of both sides, we get ln of 3x, or 3 to the x, but I'm going to take this x and put it out front. So x ln of 3, and then over here we have ln of 4. So now I can divide both sides by the ln of 3. So we see x is equal to ln of 4 over ln of 3. And if we wanted to, that's our exact answer. We could get an approximation of this. ln of 4 divided by ln of 3. Is approximately 1.262, it rounds to, because this was a 1 and then followed by an 8. So if I'm rounding to the third, I would look at what follows the 1, and that makes it a 2. And so this is the solution I have for this. This one was almost kind of hidden from us, but it was eventually in more of a quadratic form. It had a pattern where we had x, and then this was like 2 down from that, because you would have 1, 0, and then negative 1. So it did have that pattern, but a little bit harder to see on this one. As we know, exponential equations are a great way for us to measure population growth because it has that exponential aspect to it. Population growth and any kind of growth of that kind. So we're going to look at just a story problem involving this, where we're going to compare the population growth rates of Pakistan and the United States. You can see that and this is in 2010, and so they measured the growth rate of that year. And we started off with 308 million, and then Pakistan had 185 million. But their growth rates are different. Pakistan's is it's more than twice the rate of the United States rate of growth. So even though we have almost half the population, or Pakistan has half the population of the U.S., with that annual population growth rate, we're going to look at a few problems one being, and we're going to use this model, this alternative population model, where P is the initial population and T is time in years since 2010, assuming the growth rate for each country stays the same. So we are making that assumption there. But we're going to compare and estimate the populations of each country in 2020, which would be last year, in the time that this was recorded in late 2021. And in what year will the population of the United States be 350 million? And in what year will the population of Pakistan be the same as the population of the United States? Okay, so we're going to use this given model, and here our starting point is 2010, right? So when we think about time, we're thinking about it from that point. And our numbers are going to be in millions, so we don't have to put the actual 6 zeros. We'll just interpret our answer to be in millions. So my P sub O, my starting point of 2010 for the United States, is going to be 308. And then for Pakistan, well, we'll do U.S. first here. And then the rate of growth, R, was 0.091. And actually, that's incorrect. Let me fix that. I was going off my memory there, but that would be a 9% growth rate. That's obviously not the case. If we go back to the other side, we see it's at 0.9%. So just slightly less than 1%. Slightly less than, 1%. We're at 0.9%. And and then 10 years. So our time is going to be in years since 2010, right? So this is our starting point, 308. So looking at this, the time, 2020, would be 10 years since 2010. And so we want to use the population in 2010 as kind of our starting point, 308 million. 1 plus our rate of growth, which is 0.009, and then raised to the t power, and in this case, that is 10. All right, so there we have it, and putting this into our calculators, do so as well, so we can get so you can see if your answer is matching up with what we end up getting. And running this calculation, you can pause this if you want to wait, but the answer you should get, 336.87 million is the prediction for 2020. Let's look at Pakistan's. For Pakistan, we have a different initial growth. It was 185 million. Let me go back and just double check that. And 185, and there's this 2.1%. That's where I was getting that 9.1. All right, so, and their rate, let's not do that. I just was writing out the values of my variables. Our R in this case is 2.1%, so 0.021. And so let's find the P sub 10 for Pakistan, starting at 185, 1 plus 0.021, parentheses raised to the 10th power, and we'll do our comparison there. And you should get 227.73 million people in 2020. All right, so very interesting. We see that they are getting closer to each other in value, because one is, Pakistan is growing quicker, more than twice as quick as the U.S. So now we're only about 100 million different from each other, approximately about 110 million or so, where before it was like 50 million or so. So they're getting closer. Let's go to the second part of this problem now. we want to solve for t to find out when exactly the United States population will be at 350 million. All right, so going back to the function that we had here, p sub t, and then p sub o, 1 plus, and then this was, well, 1 plus r raised to the t. And we're given 350 as my answer, right? So we're going to start off. Again, we're assuming this starts in the year 2010. Our rate of growth, assuming it's the same, 0.009. T remains now my only sort of variable that I have, and I'm going to use logs to help us find that. So first off, this 1 plus point, that just becomes 1.009. Much easier just to write it that way. Let's get the exponential part of this isolated. Remember, that was one of our big steps that we have for exponential equations, is get the exponential statement isolated. And so we're doing that here. And we have 350 over 308. I'm going to leave that like that, because most likely it's going to give me a decimal. So if we avoid rounding until the very end, that can be a really helpful thing to us. We won't round early and then round again. And as long as we can avoid rounding mid-process, the more accurate our final answer can be to whatever number of decimals they want it to be accurate to. So if you round now and then round a second time when we get to the end, you might end up over-rounding. All right, now we'll take the ln of both sides, or you could do the log of both sides. Either way is fine. So we have the ln of 350 over 308 equal to, and now that I've taken the ln, I'm going to write the t out front. So we have t ln of 1.009. And now I can solve for t. So t will be equal to the ln, the ln of 350 over 308 divided by the ln of 1.009. Working that out, putting that into our calculators, go ahead and follow along as well. You should get 14.26. So that's like 14 years and then about a quarter into that 14th year. So it's going to be somewhere around 2024. So we add 14 and 25. That's when we'll see that population hit the mark of about 350 million. On the last part of this question, it says to solve for t to find when the population will be the same in the two countries. So our two population functions for the U.S. Was piece of t equal to 308 times 1 plus, or 1.009 to the t power. And then for Pakistan, piece of t 185, and again we're starting it in 2010, and this is 1.021 raised to the t. And we want to know when will these be equal to each other. I'm going to say this is P1, that's P2. So we want to know when will the population for the U.S., P1 of t, be equal to the population of Pakistan, P2 of t. And so we can just actually take the function there, 308, 1.009, this would be the United States population growth formula, and set it equal to the Pakistan growth rate formula. and then begin the process of trying to solve for t here. So one way to kind of simplify this out would be to, let's kind of get rid of some of the numbers that we have here. And by get rid of, we really need to sort these things out. I need to get the t stuff to one side, stuff that's being raised to the t power to one side, and then the numbers to the other side, right? The numbers that are by themselves. So if I divide both sides, let's just pick one of these two sides. I'm going to divide both sides by 185. So I do it here, and then I do it here as well. And then that will essentially get rid of the number I have here on the right-hand side, but it still leaves me with this part on this side. So I want to get rid of the t power part on this side. So I'm going to divide both sides by 1.009, which will cancel this out. And then on the other side, it doesn't cancel out, but that's okay, because it's I don't need it to cancel out. I want the t on that side. So this leaves me with just the numbers, the 308 over 185 here. And then on the other side, I've got, and I can write them as one fraction, 1.021 over 1.009, all or both raised to the t power. And we know that because a over b to the m power is equal to both of these raised to the same power on top and bottom. So we just kind of did that in reverse here, wrote it as one power. Well, now finally, I can actually get rid of, or get the t out of the exponent there by taking the ln of both sides and then moving the t out front. So that leaves me with t ln of 1.021 over 1.009. And then we have the ln over here of 308 over 185. So t then is going to be equal, if I want to get rid of it, got to divide both sides by this, the ln of, you can see what I'm going to do here. And this is going to give me my final answer. T is going to equal the ln of 308 over 185 divided by the ln of 1.021 over 1.009. And then we can find what the approximate t is. How many years t will it take to get to the same population level? Go ahead and punch this into your calculator. Pause if you want. And we should get 43.11, or actually 12. So just a little bit after the 43rd year, which would be the 44th year. I think I interpreted the previous one incorrectly, but so 43 years it'll take for their populations to be really close to equal, and then once we push it over into the next fraction of a year, which would be the 44th year, 44, so that would be 20, after 2010, it'd be 2054 is the year where we will see, so 2053 would be the year where we're just barely, we're only 1/12 of the population difference, but once we get to 2054, of course these are estimations because lots can change within that time period about population growth, etc. Maybe another worldwide coronavirus, just to pull an example out of the hat. But this would be the year that they would have equal populations. All right, now we're going to take a look at solving some logarithmic equations. And of course, previously we were looking at exponential. We know these all have things in common with each other. Both are inverses of each other. But this is just a sampling of the types of what might be considered a log, or what would be considered a logarithmic equation. It's some log statement set equal to something else, or maybe a log statement set equal to another log statement. Maybe they both have the same base. Or you can have a couple of logs set equal to some number, right? The idea of a equation, and specifically a logarithmic equation, is that there is logarithm statements, and they are set equal to something. So there's an equals in there. And then our goal usually is to figure out what is the value of x that will make this particular equation true. For example, the first one we have there, log base 2 of x equaling to 4. Many times we can solve it by putting it into exponential form. My base is 2. This is the outcome of a log statement, so it's an exponent. So literally it's 2 to the 4th power, and we see that x is equal to 16. So log base 2 of 16 is equal to 4. And you can try that out. Remember our change of base equation that we had. We can take any log, so log of 16 divided by the log of my base 2 should equal 4 in this case. You can check that out and see that it does work. The log of 16. And notice that my bases are different in this thing. There's no base written, so we assume it's log base 10. So we're using the log on our calculator. Log base 10 of 16 divided by the log base 10 of 2. And we get 4. And you can do it with ln as well. So this would also work with the log base e, ln, divided by the log base e of 2. This also, both of these gives us 4. All right, so here's another problem, equation involving a logarithmic statement. Just like we wanted to get the exponential part by itself, we're going to want to get the log statement by itself if possible. And we only have one, so we should be able to do that. Let's subtract 4 on both sides. That gives me 3 log base 2 of x equals negative 3. And then we can divide both sides by 3. And that leaves me with log base 2 of x equaling negative 1. And so now I can take a look at putting this into an exponential statement. My base is 2. The answer of a log is a power. And it equals whatever we're taking the log of. So x is equal to 2 to the minus 1, which is the same as 1 divided by 2 to the positive 1. So x equal to 1/2. And then we can check our thing by plugging it in. So if I have 4 plus 3 times the log base 2 of 1/2, do I get 1? And so if I'm going to plug this in as it is, using the change of base, this would be 3 times the log of 1/2 divided by the log base 10 of 2, and equaling 1. So let's see if we can do that. If I go 4 plus 3 times the log of 1/2 divided by the log of 2. What do I get? Well, this all comes out to be equal to 1. See if you can plug that into your calculator and get the same result. So we can say that x is equal to 1/2. So in those examples, we looked at how to, one of the ways to solve logarithms is to rewrite them as exponential. But sometimes that's not going to be our best strategy. One of the other properties we have with logs is the one-to-one property, which basically says log base a of m, if log base a of m equals log base a, so the same base of n, then m has to be equal to m. So they have to be equal to each other, right? If their logs are equal, then the expressions would have to be the same as well. And so we're going to use that property here as well. I'm going to rewrite these a little bit, but you'll notice that as we're starting off, these are all log base 4, so we have the same base for each one of these. On this side, we have a sum of two logs that are both base 4. And so if I want to, I could condense those, right? Here we have them in expanded form where they're being added, but we can write it as log base 4 of one product x times x plus 1. So I took the two parts that we're taking the logs of, and we made them into a statement of a product. Which, remember, when we expand a product, we write it as a sum. With a subtraction, sorry, that's not what we have here. We also have an addition. But if it was a subtraction on the other side, which we don't have that, we have an addition, we could write it as a quotient, division. But this also would just be the log base 4 of the product of these two, log base 4 of 6 times x minus 1. Okay, and notice that, so we have the log base 4 over here, log base 4 over here, and then we have these expressions. And so I need to really figure out, how do we make x times x plus 1, the expression x times x plus 1 that I'm taking the log of, equal to 6 times x minus 1 when I'm taking the log base 4 of on the other side. So we can kind of just ignore the logs at this point and focus on, how do I make the left-hand side expression equal to the right-hand side expression, the n equal to the m. And expanding this out, this would be x squared plus x. On the other side, I have 6x minus 6. So we have a quadratic that we need to solve. I'm going to subtract 6x. We need to set it equal to 0. And then add 6. So I have x squared. Positive 1 minus 6 is minus 5x. And then we had plus 6. And now we have 0 over here because these both canceled out, which is what I always want to do in solving a quadratic, is get it set equal to 0. My signs have to be the same because I have a positive product here. So x and x, they both have to be the same sign. I know they're both going to be negative because the sum of the inners and outers need to be negative as well. And 2 and 3 looks like this might be the winner. Negative 2 plus negative 3x gives me negative 5x. So I have my two solutions. X are equal to 2 and to 3. And we need to check these. So I'm going to go back to my original expression, and we're going to plug in 2, and then we're going to plug in 3 and check these out. So using 2, this would be, we've got the log base 4 of 2 plus log base 4 of 2 plus 1, which would be 3. And then on the right-hand side, I have log base 4 of 2 minus 1, which is 1, plus log base 4 of 6. And we can plug these in and use our change of base thing. This would be log base, or just log of 2 over log of 4 plus log of 3 over log of 4, log of 1 over log of 4 plus log of 6 over log of 4. Or you can use ln. Let's check each side and see if we get the same sum on either side. After plugging those in, you should get the similar statement there, or a similar outcome, 1.292 approximately on each side. Great. Let's jump into the other one. I'm going to change colors here and try to not expand it out so much as I did before for the other side. So plugging in 3 as a solution, This gives me log base 4 of 3 plus log base 4 of 3 plus 1, so 4, equaling log base 4 of 3 minus 1, so 2, plus log base 4 of 6. And we're working these out then. This would be log of 3 over log of 4 plus log of 4 over log of 4. And I'm just going to use the same stuff that I had because it's basically the same setup. You know, everything's divided by the log of 4. Log of 6 over log of 4. Sorry, need to do these first. So if you hit second entry, you can just go back and change the top numbers in these because basically they're the same setup but just different number outcomes. In fact, it's true on both sides as well. So hit second enter on your TI and you should be able to just go back and change those top numbers. And in plugging those in, checking them, you should see that both sides come out equal to 1.792 in both equations. Now, I'm going to go back a little bit here and show you how we might have given ourselves a little bit of a shortcut here. I'm going to go back to this stage before we actually plugged in all those logs. And I want to use our expansion condensing rules here just to kind of see that we can see that they're going to be equal. Like, for example, here we're adding the two logs, so we could rewrite that as the log base 4 of the product of those two, 2 times 3. And here, the log base 4 of the product of 1 times 6. And we can see that this is going to be the log base 4 of 6 equals the log base 4 of 6. So, bada bing, bada boom, they checked out. Same over here, this would be the log base 4 of, we're adding these, so again, multiply 3 times 4, equaling the log base 4 of 2 times 6. So that's the log base 4 of 12, and the log base 4 of 12 as well. So again, these should come out equal to each other, and so we would say these are both solutions to the equation. Okay, we're going to take a look at a couple more, just examples for us to go through. On this first one, we have, well, actually, both of them have both log base 2s. And this is just, we're going to practice using those product and those quotient rules. On this first one, A, we have an addition, which is going to equate to a product. So log base 2 of x minus 3 plus log base 2 of x minus 4. And this is equal to 1. So if I rewrote this as a using the quotient or the product rule, this would be log base 2 of x minus 3 times x minus 4. That's equaling 1. And we could multiply that out, so log base 2 of x squared, and then my inners and outers, negative 3x, negative 4x, give me minus 7x, and then plus 12, equaling 1. Now this sounds a little counterintuitive, but let's rewrite this as an exponential statement. So now we're kind of, we've done the quotient rules and all that, and the product rule. Now let's combine that with rewriting this. Again, the base is 2. Here's the exponent, so 2 to the 1 equals what I'm taking the log of, x squared minus 7x plus 12. See, some of this stuff just requires trying things out, being creative, knowing all these rules. 2 to the 1 very nicely gives us just 2. And so I can subtract this to the other side, and now I have a quadratic equation set to 0, x squared minus 7x plus 10. And we can factor it and see what we can come up with here. So we know it's xx. We know it has to be minus minus because we have a positive here. So the signs have to be the same, and we have a negative sum here. 2 and 5 is going to give me that product of 10 and sum of 7. So we see x is equal to 2 and to 5. So now let's check those answers. So starting with 2, this would be the log base 2 of 2 minus 3, which is negative 1. Because we're substituting 2, right? So that's 2 minus 3. Plus log base 2 of 2 minus 4, which is negative 2. And this is supposed to equal 1. If we wrote this as a quotient, this would be log base 2 of negative 1 times negative 2, which is positive 2. Equal to 1. So we can see how we got 2 as a solution, because once we've done that multiplication, the two negatives become positive. We have 2 to the 1 power equals 2. Yes, that's true. However, it was only when we put this into the multiplication form, into the product form, that this worked. If we try to take the log base 2 of negative 1 or the log base 2 of negative 2, you can see that we're going to end up with error here and error here. We cannot take the log of anything negative. In other words, 2 to what power is going to give me negative 1? There is no number. There is no power that I could take 2, that I could raise to 2 to get negative 1 as an outcome. And so when we multiplied them, yes, they became positive. But it has to work at every stage, right? And so because it doesn't work at this stage, this is not a solution. It doesn't work because that didn't work. But let's go ahead and try 5. Plug in 5, I get log base 2 of 5 minus 3, which is 2. And then log base 2 of 5 minus 4. 5 minus 4, of course, is 1. So I'm doing these in my head and putting 5 minus 4. That's 1. And this is equaling 1. So simplifying these out, well, actually, change this to a multiplication. Log base 2 of 2 times 1 equaling 1. So that's log base 2 of 2, which 2 to the 1 power equals 2. This works. And it would work back here as well. This would be, this actually here would be 1. And it says plus 2 to the what gives me 1. The only power, in other words, 2 to the what results in 1. The only thing that works there is 0. So that's 1 plus 0, which is 1. So at any rate, we weren't taking the logs of anything negative. So in this case, 5 is my only solution. One of the things you want to do, as you can see here, when we go from addition to a multiplication, that we can end up with an incorrect answer that works at this level, right? This would work here, but it doesn't work here. So one of the things that we have, if we're solving a logarithmic equation, we need to check the answers that we get. All right, let's work that second one. This one actually has a subtraction that is occurring. And so with that subtraction, we know we can rewrite that as a quotient. In other words, log base 2 of the first one, x plus 4, divided by log base 2 of x plus 3. So x plus 3 will go down here. And this is equaling 1. All I did was rewrite this as a quotient on the other side there. And just like before, let's rewrite this as an exponential statement. 2, so my base, to the exponent, the solution of the exponential equation, 2 to the 1, equaling x plus 4 over x plus 3. All right, well, now this is kind of a regular equation that we can solve for. I can get rid of the fraction part. We know here that x cannot equal negative 3. This is one of my solutions that is not allowed, okay? Because we could not have negative 3 on the bottom there. So I'm just putting that as an aside. We'll multiply both sides by x plus 3. We'll distribute the 2, so that's 2x plus 6 over here, equaling x plus 4 over here. And now let's solve this baby for x. I'll subtract x, get rid of x's on the right-hand side, and then subtract 6. That actually leaves me, I'm going to erase the 4 here. I was going to bring that down and rewrite it, but we did this in one step. We get negative 2. So we see 2x, this is going away. 2x minus x is 1x. So we have x equals negative 2. Okay. Well, does this check? I'm going to check this. I don't think yeah, okay, here we go. So I'm going to rewrite this, and then we will plug in negative 2 here. So log base 2 of negative 2, negative 2 plus 4 is 2. Log base 2 of negative 2 plus 3 is 1. And so we're okay here with we have positive numbers in there. That's good. Log base 2 of 2, we know this is 1. And log base 2 coming out with a 1 is 0. 2 to the 0 is what gives me 1. 1 minus 0 is 1, so yes, this checks. So x equal to negative 2 is one of my solutions. Let's look at an application using logarithms. And this is a logistic involving logarithms growth model. It says, suppose the carrying capacity M of the human population on Earth is 35 billion people. And in 1987, the world population was about 5 billion. Sounds about right. Use the logistic growth model of P.F. Verhulst, hopefully I'm saying that same, sounds very German, to calculate the average rate K of growth of the population, given that population was about 6 billion in 2003. So one of the knowns that we have here is the M, right? M is kind of a consistent number that's going to be, M is that 35, the maximum carrying capacity of the Earth. And then we have some other stuff. We have 5 billion in this year, and then we have 6 billion in this year. So, and what we're really after ultimately here is K. So there's a couple of things that we need to find. I need to find an A value, and I need to find this K value. Well, ultimately I need to solve for K. So really I'm going to have to find A first. And so we have our kind of starting point here, which is our 1987. So we're going to put that as time equal to 0. Time equal to 0 is 1987. So P sub 0 at that date, the starting point, we had 5. So P sub 0 was 5. Population at time 0 is 5 billion. This is in billions. This is in billions as well. So we have matching, what the numbers are going to be. So let's start off, and we're going to use that first P sub 0 to help us find A. Given the stuff that we have, and all I'm doing is pulling this from one side to the other here. Given that we have these things, I can first just we can put 5 in for my P sub 0. So P sub 0 equals 5 with 35 over the top there, and then 1 plus A e to the negative K, and we're at time 0, right? Because that's my piece of 0 here. This is important, this piece of 0, because that makes this e to the 0. So let me just kind of simplify this for you up here. E to the minus k times 0. Well, k times 0 is 0. And e to the 0, any number to the 0, is 1. So now what I have is 5 equals 35 over 1 plus a times 1, or just 1 plus a. And so now this is just a matter of solving this particular equation for a, which will give us the one variable that we needed to find there to have our formula adapted to the situation. So if I multiply both sides by 1 plus a, that gives me 5 plus 5a. And here that's equal to 35. Subtract 5. Subtract 5. Looks like I was dividing there. But I have 5a is equal to 35 divided by 5, or 35 minus 5. That's what I didn't want to do. Which is 30, and now I can divide by 5. We can say that a is equal to 6. 30 divided by 5 is 6. So I further have my formula here for this situation. M is 35. 1 plus a is 6. So we have 6 in there times e to the minus kt. We still need to find the rate of growth, right? That's my next goal here, but we're one step closer to that. So cleaning off our slate here a little bit, let's now for 2003, which is 16 years following 2020, what was it? 1987. So that's 16 years after 1987. Because if you go 2003 minus 1987, you can kind of see if we do some subtracting here. 13 minus 7 is 6. 9 minus 8 is 1. And that becomes a 9, and that becomes a 1. So then we have 0, 0. So 16 is my difference there. So, we're going to now put 16 in for my piece of t. We have 35. Oh, I'm sorry. No, 16 is not. Sorry. Let's go back. We're going to find the p of 16, which we know to be 6 million or 6 billion. So I'm just going to put that as my answer there. And then let's fill in the rest so we can find the rate of growth. 35, and then I have 1 plus 6 e to the minus k, but our time here is 16t. So I put in 16 for the t, so I'm now putting it into the function here. And so let me rewrite that. 6 equals 35 over 1 plus 6 e to the minus 16k. In a similar way, let's get rid of this denominator stuff. Multiply both sides by 1 plus 6 e to the minus 16k on both sides. And that cancels out over here. I have 35 equals 6 times that. I'm going to divide both sides by 6. So we can just have the 1 plus 6e to the minus 16k. And here we have 35 over 6. I'm going to subtract 1 and get rid of that. So I'm trying to get the e by itself first here. So I have 6 e to the minus 16k equaling 35 over 6 minus 1, so let's make that 1 6 over 6. Common denominator, this gives me 29, carrying the denominator 6. So we have 29 over 6. And if I want to get rid of this 6, we can divide both sides by 6 again or multiply by 1/6, same thing. Division by 6 is the same as multiplication by 1/6. And so this gives me, let's rewrite the whole thing here, e to the minus 16k equals 29 over 36. Oh, okay. So then let's go ahead and I'm going to move this over here, capture this. We're just going to move it over here so we can solve it. And now I'm going to take the ln of both sides. Oops. So taking the ln of both sides, that's the log base e of e to that. So that leaves, and I do it to both sides. So that leaves me with minus 16k equaling the ln of 29/36. And k then will be equal to the ln of 29/36 divided by negative 16. And so here's where we turn to our calculators. ln of 29 divided by 36. Divide that by negative 16. We get 0.0135. 0.013. Let me make sure that's a 5. Yep, 5 rounds down, stays as a 5. So the rate of growth appears to be 0.0135 or 1.35%. So our current rate of growth appears to be about 1.35% for the world as a whole. For the last part here, we're just going to look at a couple of inequalities, both a exponential inequality and a logarithmic inequality. We follow the same rules, right? We kind of act like it's just an equals there. There's nothing really different except for the fact that if we multiply or divide by negative on both sides of the equation in the process of solving it, we have to flip the inequality symbol around. So for this first one that I have here, I'm just going to get that exponential part by itself. So starting out, I'll probably just subtract 3 on both sides. That gives me 5 times 0.07 to the x is less than 15. And then let's get rid of that division or that multiplication by 5. So I'll divide both sides by 5. 0.07 to the x is equal to, it's not equal to, but rather less than 3. And then let's go ahead and take the log of both sides. And that takes this x and can bring it out front. So I have x log base 10 of 0.07 less than, keep on doing that, log base 3, or log base 10 of 3. And then let's solve for x. I'll divide both sides by the log base 10 of 0.07. So I have log x is less than log base 10 of 3 divided by log base 10 of 0.07. Oh, I'm sorry. I've switched to 0.07. That's completely wrong. So let me go back and just fix that. We haven't done that yet, but that would have made a big difference. So we'll just put this as 0.7. Fix that. 0.7. And yeah, we need to do that here, here, and here. This is why it's always good to use pencil when you're doing math. I know you've probably heard that before, but perfect example, of course, I'm using a pen, but it's an electric pen, or electronic pen, I should say. So, at any rate, let's go ahead and do that, get the approximate value here. Log base 10 of 3 divided by log of 0.7. And we get negative 3.08 as my final answer there. And so all the x values that are less than that will be part of the set of solutions for this inequality. Any x values that are less than approximately negative 3.08. Putting that as a interval notation, this would be negative infinity all the way up to negative 3.08, not including 3.08. So graphically, of course, at negative 3, negative 2, negative 1, and 0, we would have a parenthesis here at negative 3.08, so almost at negative 3, with our arrow shaded to the right. Shaded to the left of that expression. What about an inequality that involves a log, so a logarithmic inequality? One of the things that we have to do, again, as we were talking about with logarithms, is make sure my expressions don't turn out negative. In other words, when we look at what we're taking the log of here, we need to make sure that 2x minus 5 is always positive or always greater than 0. So we need to talk about the domain here, because we do have a definite domain where we cannot take the log of anything negative. So as putting this greater than 0, it also cannot be 0. I can't take the log of 0. It has to be more than 0. So I'm going to find the domain, adding 5 to both sides, divide by 2. So we know that x has to be greater than 5/2. So we're starting off with that knowledge because we want to find the solution set of this. This is part of that. This is knowing that I can't have any numbers that are less than 5/2 or 2.5. They have to be greater than 5/2 or 2.5. Okay, well, let's continue now in solving this. And we're going to do this by doing something we haven't really done before yet, and that is to put both of these up into the exponents, which is a little like rewriting, but in other words, what I'm going to do here is raise both of these into the exponent of 10. And we'll see here why I'm doing this here in a second. So in other words, 10 to what I had there, the log, is going to be less than or equal to 10 to the 1. So I just put these up into the exponents. Main reason why I wanted to do that is because this is log base 10. We just aren't writing that there. And we saw from one of our logarithmic rules that if I have that, then my expression, 2x minus 5, is the rewriting of that. And so that gives me, I can just take that out of the exponent. And the 10 raised to the log base 10 kind of goes away. And I'm just left with this statement, which is a very simple inequality statement. If I add 5 to both sides, that gives me 2x is equal to 15. And then divide by 2. We see that, this is a less than or equal to. I haven't multiplied or divided by a negative. I just see that x has to be less than or equal to 15/2. So I have to meet this requirement as well as this one. That's kind of an and statement here. In other words, my solutions have to be, solutions x have to be less than or equal to 15/2, and x has to be greater than 5/2. There are two The solutions lie there, and they have to meet both requirements. I can't have something that busts my domain, but these also are the ones that give me values less than or equal to 1. This, of course, is 7.5, and this is 2.5. So I'm going to plot these out. We'll start with 1. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 over here. So 7 halves would be right about here. 7.5, sorry, which is 15 halves. And this would be a bracket pointing to the left. And 5 halves would be at 2.5, so that's right about here, 5 halves. This would be a parentheses pointing to the right. With an and statement, we see that the solution set here is the areas where they cross over, because it's the and statement, it's the intersection of these two. So we see that my solution set lies from 5 halves all the way up to 15 halves, including 15 halves. So with the log inequalities, we have to take a couple of things into consideration. We have to figure out what log values are not allowed, because so we need to figure out the domain, in other words. And then we also have to solve, and then we take the intersection of those numbers for our solution set. So with log equations, we need to test our answers to make sure we don't get something negative. We can't take the log of something negative, so if we have expressions, we've got to plug them in and see what we get with those. Also, when we're doing log inequalities, we need to find the domain of those inequalities, and then the solutions, and then find their intersection. Exponentials were not as involved. For exponential equations, so I'm trying to go back there. Where'd it go? Okay, here we go. We just had to solve it. We didn't necessarily have to plug it in or find the domain, because x as an exponent, this can be negative, it can be anything. So there's no restrictions, but we do have restrictions with logarithms. So we kind of like we did with square roots, we always have to make sure we have those. Also, in general, as we're solving for exponentials and for logs, we like to get them alone and condensed if possible. So if they're expanded logarithm statements, we want to try to condense them. If they're exponential statements, we try to get the bases isolated to one side. And then a lot of times we can use logarithms to find those solutions. Good luck practicing these, and we'll see you on the other side.